All right, let's talk about something really important for keeping any Linux server online and kicking: network bonding. It's one of those core technologies that once you get it, you'll see why it's absolutely everywhere. So let's dive right in. So picture this. You've got a critical server, right? It's humming along, doing its job, connected to the world with just one single network cable. Now, what happens if someone trips over that cable? Or the port on the switch just dies? Or the network card itself decides it's had enough? Well, for most setups, the answer is pretty brutal. Your server is offline, instantly. And that right there, that's the core problem we're here to solve. A single network connection is a single point of failure. It's the one weak link in what might otherwise be a super robust system. But what if? What if we could just get rid of that weakness altogether?
Well, this is where network bonding, or link aggregation, as it's also called, comes to the rescue. It's such an elegant solution, really. We take multiple physical network cards, multiple NICs, and we just tell the Linux kernel, hey, treat these as one single, much more powerful and way more resilient interface.
So here's the basic idea. You take, let's say, two physical interfaces, ETH0 and ETH1, and you plug them both in. The Linux bonding driver then swoops in and virtually bundles them into one logical interface, which we usually call something like bond 0. Now, as far as the rest of your operating system is concerned, it just sees one super reliable connection to the network. Simple as that. So why do we even bother with all this? Well, it comes down to three main goals. First, and maybe most important, is high availability. If one of those physical links fails, traffic just automatically moves over to the other ones. No downtime, zero. Second, load balancing. We can spread the network traffic across all the links so no single one gets totally swamped. And third, increased throughput. You combine two 1 gigabit links, and suddenly you have a logical pipe that can push up to 2 gigabits. Awesome. And let me be clear, this is not some obscure niche trick. This is bread and butter stuff for reliability in modern data centers. It doesn't matter if you're running on bare metal servers, virtual machines, or even Kubernetes nodes. Preventing an outage just because one cable failed is absolutely mission critical. But here's the thing, not all bonding is created equal. Linux actually gives us a whole toolkit of different modes, and each one has its own special strategy. So let's take a quick tour of the most common ones.
First up is Mode 0, also known as Round Robin. This is about as straightforward as it gets. The kernel just deals out packets to each interface one by one. Packet 1 goes out ETH0, packet 2 goes out ETH1, packet 3 goes back to ETH0, you get the idea. It's a really simple way to make sure you're using all your available links.
The big upside here? You can get a serious throughput boost. But, and this is a big but, it comes with a couple of major gotchas. First, your network switch has to be configured to play along. It needs what's called port trunking. And second, because packets for the same conversation can take slightly different paths, they might arrive out of order. And that can really mess with some protocols, like TCP. Next, we have Mode 1, Active Backup. This one is all about pure, simple, high availability. The concept is dead simple. Only one interface is active at a time. The other one just sits there, completely idle, kind of like a standby generator, just waiting for something to go wrong. If that main link fails, bam, the bonding driver instantly flips over to the backup link, and traffic keeps flowing. The beauty of this mode is its simplicity. You don't need any special, expensive managed switch. It just works. But the trade-off is huge. You get zero performance increase. Your bandwidth is always limited to whatever a single link can give you. This mode is all about reliability, not about speed. Okay, now for something a bit smarter. Mode 2, or Balance XOR. This is a much more intelligent way to load balance. Instead of just cycling through interfaces, it does a little bit of math, a hash calculation, based on things like the source and destination MAC addresses. This math ensures that all the packets for one specific conversation always travel over the same physical link. So what's the point of all that? Well, it totally solves that out-of-order packet problem we saw with Round Robin. You get solid load balancing and failover. But just like Round Robin, you're going to need to get your hands dirty and configure port trunking on your switch. All right, now for Mode 3, Broadcast. And this one's a bit of a weirdo. It provides fault tolerance by doing something kind of extreme. It sends every single packet out of every single interface in the bond, all at the same time. The upside? You get insane redundancy. If one link fails, who cares? The packet already went out on the others. The massive downside, of course, is that it's just incredibly wasteful. You get no performance gain, and you're just spamming your own network. You almost never see this one, but it exists for those situations where you need fault tolerance at literally any cost.
Okay, now for the big one, the one you'll see out in the wild all the time, Mode 4, which uses the 802.3ad standard. You'll probably know it as LACP. This is the industry standard, and for good reason. It's a dynamic protocol where your server and your switch are constantly talking to each other, negotiating which links are active and how to balance traffic across them. This is the mode for pretty much any professional production environment. It's a fantastic mix of smart load balancing and automatic failover. The only catch? Your hardware has to be up to the task. You absolutely need a managed switch that supports LACP. Now for a pair of really clever modes that don't require any special help from your switch. First up is Mode 5, or Transmit Load Balancing. With this, the bonding driver intelligently spreads out all the outgoing traffic, making sure to send new packets down whichever physical link is the least busy at that exact moment. The advantage here is pretty obvious. You get some nice load balancing for your outgoing traffic without ever having to touch your switch configuration. But there's always a but, right? It only works one way. All of your incoming traffic still gets funneled through a single primary interface. No balancing there. And that leads us perfectly into our last mode, Mode 6, Adaptive Load Balancing. This basically takes Mode 5 and says, I can fix that. It gives you the same smart transmit balancing, but it adds this really clever trick using ARP negotiation to also balance your incoming traffic. It basically fools other devices on the network into sending their traffic to different physical interfaces on your server. So this is kind of the holy grail if you're working with a simple, unmanaged switch. You get balancing in both directions. Its main downside is just that, well, it's complex. Because it relies on all this art magic, it can sometimes be a real headache to troubleshoot if things go wrong. Okay, that was a lot. Let's put it all together and look at them head to head. This table really breaks it down. You'll notice every single mode gives you redundancy. That's the whole point. Now, if you want performance, you're looking at modes 0, 2, 4, or 6. But the real deciding factor is often the switch. If you have a powerful, managed switch, Mode 4, LACP, is the gold standard. If you don't, then Mode 6 is probably your best shot at performance. So let's distill all this down into a simple, practical playbook. What should you actually use? Honestly, for about 99% of cases, it comes down to just two choices. If all you need is simple, rock-solid failover, and you want it to just work with any hardware, use Mode 1, Active Backup. But if you're in a production environment and you need both performance and redundancy, the answer is almost always Mode 4, LACP. It's the standard for a reason. And remember, this isn't just for old-school bare metal servers anymore. These same principles are absolutely vital when you're setting up virtual machines in the cloud or making sure the nodes in your Kubernetes clusters are as bulletproof as possible. True high availability really starts at this network layer. So there you have it, the whole bonding toolkit, from the simplest failover to dynamic, high-speed aggregation. The key thing to remember is that you now have the tools to get rid of a huge single point of failure in your infrastructure. So the only question left is, what are you going to do with them to make your own network truly resilient?